So, hello everyone. So, welcome to lecture 46. So, with the previous lecture where we have actually seen the origin of dissipative properties, the Onsager's linear response theory, and so what sort of dissipative properties can Onsager's theory explain. The resistivities, the conductivities, the thermal conductivities, the diffusivities, the electromigration, the Peltier, the Seebeck coefficients, which from which come the Peltier and Peltier effect, Peltier refrigeration, and the thermocouples, and so the electromigration and piezoresistivity and so on and so forth. We put a stop to our discussion on the dissipative properties, right? And we ended the last class by asking the question, so we looked at dissipative properties as something where I apply a constant force and I generate flux, right. So this force is not by no means some sort of a time varying force or whatever. I just apply a constant force and I look at the flux that is happening. So if there is flux upon constant force, then those forces tend to be dissipative. And similarly, in an equilibrium property case, I apply constant force and so the springs should stretch and nothing else should happen. So there is storage of energy, but so again upon constant force, so nothing is happening, it is at equilibrium, right. So but if I release the force, it will come back to equilibrium, right. So those are the equilibrium properties that store energy, but so far I have not been looking at the dynamics, right. What happens if I so in case of polarizations, let us say if I start oscillating the electric field, then polarization also oscillates, right. So let's take the simple example of a dielectric material. So dielectric material is in green, right, and this dielectric material is surrounded by two electrodes, right. So this is an electrode 1, this is an electrode 2, and here to this electrode I apply an AC voltage, right. So I now let there is this some sort of a polarization is created inside. So some sort of polarization is created inside these dielectric materials, right. So by application of electric field, and because the electric field itself is oscillating in time, the polarization also, which is the response, right. So the electric field versus time, polarization also, which is the response, which is in red here, starts oscillating in time. Okay. So this is the material response. Polarization is oscillating in time as electric field is oscillating in time. Electric field forces the polarization to oscillate, right. So polarization is now no longer a constant, it is oscillating up and down with respect to the electric field, or it is oscillating from so up to down polarized to up polarized to down polarized and so on and so forth with respect to the applied electric field, right. So it follows the applied electric field in some sense. Okay. So now because of polarization oscillating up and down, I have charges that I put on the metallic plates. Now okay, so these are negative charges on this plate, these are positive charges on this plate, right. So to start with, right, and then once I start oscillating this electric field, these charges start also so the positive starts becoming negative, the negative starts becoming positive. So if I just look at Q on the plate versus T, the Q also starts to oscillate, right. So that is right. So whatever is positive in time t1, so let's consider this plate. So whatever is negative at time t1, at time t2 they all become positive, right. So as time evolves it becomes positive, and here it becomes negative. This is at time t2, this is at time t1, right, and so on and so forth. So there is, because of this charge flow, right. So the charge on the plate should exchange, should also start flowing, oscillating. That charge actually flows through the external circuit, right. So the external circuit, then if I am measuring some current, right. So if I put an ammeter here and measure current, I should also be able to measure current, right. So current is also oscillating or fluctuating, right. So now it is not that I do not have flux, I have flux which is sort of oscillating, right. So I have current which is going up and down and so on and so forth, right. So, I can simply so am I dissipating power, if that is the question, right. So, let us say Q equal to CV, right. So, that is, and I am oscillating V equal to V naught sin omega or cos omega t. Okay. So, I am oscillating V at V naught cos omega t. Then Q equal to, if I assume C to be a constant for the time being, C V naught cos omega t, right. So, the current then will be dq by dt, that is equal to C V naught sin omega t omega, right. Then the power that I have, the instantaneous power, is just V times I, that is equal to so C V naught square omega cos omega t sin omega t, right, in a capacitor, in this dielectric material. This is an ideal dielectric material, right. And so although I have I, Vi is this quantity, and if I look at the average power that is dissipated, right. So, that is just average of Vi. So, I just take an integral, time integral of this sin omega t with respect to dt divided by the total time, right. So, integral dt, that is the average, right. And that so integral of that just becomes an integral, time integral of sin omega t cos omega t over long time, right. So, t is long or t is infinite, right. So, in some sense this is so sin omega t cos omega t oscillates like this, right. So, it oscillates at 2 omega frequency, okay. And since it oscillates at 2 omega frequency, so I have, if I am integrating over the entire time, this is time axis, then I have positive, negative, everything sort of cancels out and this will be 0, okay. So, although I have some sort of a current, right. So, it is not just having a current, I have this oscillating current is also oscillating as I naught sin omega t, voltage is oscillating as V naught cos omega t, but in this case Vi product, the average Vi product is 0. So, this is still a conservative force or conservative quantities. What I am talking about, the properties, the capacitance is still a conservative quantity, okay. So, one should not, so here I am forcing the dynamics, right. So, I am not applying a constant force, right. Since I am applying a dynamical AC input, the output that I get is also an AC output, but that means that there should be charge motion, and charge motion is nothing but current. So, if charge is oscillating, current is also oscillating, but I look at the Vi product and I see that so the Vi product, if I integrate it over a long time and take the average of it, the average power that is given to the system is 0, or the average power that is taken out of the system is 0, right. So, the system is not at all dissipating any sort of power, right. So, ideal capacitor, it also works out when I put in some dynamics that all these conservative properties, the equilibrium properties, when I put in some dynamics, are not going to dissipate power, right. So, that stands, okay. Whereas, if I have a resistor instead of a capacitor, if I have a resistor, right, and I apply a voltage, now in a resistor V equal to IR, or GV equal to I, G being the conductance, not resistance, but opposite of conductance. And so, I have V oscillating at V naught cos omega t. So, I will exactly oscillate at G times V naught cos omega t, and if I actually look at Vi is integral of V naught square G cos square omega t dt, and cos square omega t is always positive, it can go to negative, right. So, although it oscillates at 2 omega frequency, it can go to negative, right. So, as a result, this is not equal to 0, this is always some positive number, right. So, a resistor, even in the dynamic case, right. So, I am always dissipates energy, or my average Vi is not equal to 0, is always greater than 0, whereas a capacitor always conserves energy, stores energy, right. So, my average Vi will be equal to 0, okay. So, this is how I distinguish a capacitor from a resistor. Alright. So, so let us keep that at the back of our mind. Now, I ask you the question, you know, so I have a dielectric. So using this dynamics, right. So, so now comes, you know, so everything we are going to measure it dynamically, right. So, now the question is, if I have a material which is some sort of a black box, right, in this case green box, right, and I want to measure the dielectric constant of this material. How do I measure it? Okay. So, so dielectric constant epsilon r is actually related to the capacitance, because you know, so epsilon times A by D is nothing but the capacitance, A being the area, right. So, I am going to put 2 electrodes on the top and bottom. This is electrode top, this is electrode bottom. This is the dielectric, right. So, epsilon A by D is C, or epsilon naught epsilon r A by D is C, right. This is standard electrostatics. We have seen this in the earlier part of this course also. So, I just need to measure the capacitance. I have to measure the capacitance to measure the dielectric constant. Okay. Okay. So, that is fine. Now, how do I measure capacitance? I have Q equal to CV, right. Now, I do a dynamic measurement. So, I do a dynamic measurement of capacitance for reasons that will become clear very soon. So, I do a dynamic measurement. Now, why do I do a dynamic measurement? Because let us say I apply some charge V, right. So, sorry, some DC voltage V, right. So, then the capacitor gets charged to a capacitance C, plates get charged to Q, right. I applied a constant voltage V as a function of time, right, and I have charge as a function of time, which is, you know, T, sorry, which is Q, right. Now, if the charge is not changing, right, I cannot directly measure the charge, right. If charge moves, what I can do, what I can measure is I can measure the current, correct. If there is some static charge that is, you know, on the plate of a capacitor, I want to be able to discharge it to actually see how much charge is there, right. I just cannot measure static charge unless I discharge it, right. So, I end up measuring, you know, fluctuations in charge. I should end up measuring changes in charge, not directly a static charge, right. So, I discharge it, I measure the current, I take an integral with respect to time, and I say this was the charge that was there, right. So, I can only measure charge if it is fluctuating. Right. I cannot measure something that is constant, I can measure things that are changing, right. Why? Because if charge is changing, I can put an ammeter that picks up the current, right. So, dq by dt is current, and current is picked up by the ammeter. I can measure the current, I can see how much current am I measuring and by how much time am I measuring it, and I can recalculate what is the charge, right. So, that is how I measure charge, right, very simple way of doing a charge measurement. Okay. So, but I need charge to fluctuate. Okay. So, as a result, what is one strategy? So, okay, so if charge has to fluctuate, I will fluctuate the cause, right. So, the cause is voltage. If I am applying voltage on the capacitor, the capacitor is generating charge, and if charge needs to fluctuate, for me to be able to measure the charge, I need to be able to measure the voltage. I mean, I need to fluctuate the voltage, right. What is a simple fluctuation or simple dynamics that I can put in voltage is I can give a voltage waveform which is in the form of cos omega t, right, simple. Okay. So, so I have a voltage waveform which is going as V naught cos omega t, right. Then very nice, then I can, you know, so using this trick of measuring current and integrating it, I can also measure charge. Charge will go as, you know, C okay, C V naught cos omega t right. So, Q equal to this, and so C which is equal to so I'll just take, you know, okay, so charge is going like this. I'll just take C equal to dq by dt, sorry, dq by dv, that is equal to what is it, C V naught sin omega t omega divided by dv is V naught omega sin omega t, right. So I can do this, right. So, I can look at the amplitude of the charge which is q naught, this is equal to q naught sin omega t, this I am able to measure, right, and I can measure the amplitude of voltage. So, amplitude of charge by amplitude of voltage, voltage should give me the capacitance. Okay, okay, that is all nice and you know, nice and good for a linear case where capacitance is a constant, right. So, I said q equal to Cv, right, or dq equal to C dV, that is how I wrote it, and then I said dq by dv is C. So, this is the measurement strategy that I have used. So, I change q a bit by changing V, and I look at the ratio of the changed q versus changed V, and I get C, that is the strategy, right. So, I have to wiggle q a bit and I have to wiggle V a bit, and the way I am wiggling it is I am giving a large AC signal, I am giving an AC signal to wiggle V, right, and that wiggling of V will create a wiggling of Q. So, I can measure the wiggling of Q, and by measuring the wiggling of Q I can just say that dq by dv is nothing but the capacitance, right. So, I can easily measure the capacitance, okay, good. But you know, what if Q is sorry, what if C is not a constant? And typically C tends to, you know, change the capacitance versus voltage, right. So, capacitance tends to change with voltage, right. So, generally, right, so in softer materials capacitance will decrease with voltage, because you know, so by applying voltage to the material, you know, so capacitance we said tells me about the fluctuations in polarizations, right. By applying voltage I can sort of reduce this fluctuations in polarization, I can sort of direct all these polarizations in one direction. By applying voltage I can reduce the fluctuations in polarization, in micropolarizations. As a result, C would go down. Okay. So, this is a typical characteristic of a very soft material where C goes down with voltage. Okay. Now, if that is the case, you know, I am applying C is a function of voltage, voltage itself is a function of time, right. So, now I have dq, or you know, so q equal to Cv, I start there. So, q equal to C of V dV, right. So, dq will then be equal to, you know, dV C of V dV plus, sorry, this is V, there is no dV, plus V dC, right. Now, everything is changing with respect to time. So, you know, so dq by dV will be equal to C dV by dt, yes, sorry, C, right. So, there is capacitance plus V dC by dV. So, I have to a priori, so to understand, you know, so I can apply dq, and I can, so this is, you know, so when capacitance itself is changing as a function of at any voltage V, right, or you know, so let us write it the other way. So, instead of writing it with respect to V, let us say dq by dt equal to C dV by dt, this I am applying, I know what this is, plus V dC by dt. This dC by dt I can also write it as so dC by dt, dC is changing with respect to voltage, C is a function of voltage and voltage itself is changing with respect to time. Okay. So, now if I apply V equal to V naught cos omega t, okay, so dq by dt, which is the current that I am measuring, right. So, equal to C of V, dV by dt will be so V naught sin omega t times omega plus V times again omega naught, I have dV by dt again, so that will be C omega naught V dV by dt equal to omega V naught sin omega t. So, let me write that omega V naught sin omega t, but now I have dC by dV sin omega t, right. Alright, I can measure the change in, I can measure the current through an external ammeter, but if capacitance itself is changing with voltage, what I do not uniquely get the capacitance, right. I get capacitance so the current is a sum of just the capacitance as a function of voltage and variation of capacitance with voltage as a function of voltage, right. So, now my current itself is dependent on just capacitance as well as dC by dV, right. So, I cannot uniquely determine capacitance, right. So, I cannot uniquely determine the capacitance in this case. I can measure the current, I can fluctuate the voltage sinusoidally, but I cannot uniquely determine the capacitance. Capacitance is not the slope of the Q versus the V, right. So, that is not how I get capacitance. Okay. So, this works, this experiment that I just proposed where I just give a large a voltage variation, an AC voltage variation V equal to V naught or VAC sin omega t, right. So, if I do this, well, this works if capacitance is constant, or for linear systems this works. But for nonlinear systems where capacitance or the response is a function of the force itself, C is a function of voltage, or in general response is a function of cause itself, right. So, these are nonlinear systems. Then my simple analysis of measuring charge, fluctuate the voltage, measure charge and take dq by dV, that does not work. dq by dV is actually not going to be my capacitance, right. So, I can clearly see here that dq by dV is not the capacitance, right. So, it is capacitance plus something else. Okay. So, dq by dV does not give me capacitance. Right. So, I have to do some other trick, right. And that trick, so these sort of measurements that I just mentioned are called large signal measurements. Right. So, you cannot really use large signal measurements to obtain the property, the value of property uniquely, right. You can get the total current or you can get the total charge by applying a total voltage, right. So, those sort of measurements are okay. So, you can directly measure the charge, you can measure current and you can measure the charge, right. So, you can measure you can apply input, you can measure the output, but output by input, differential change in output by differential change in input is not going to give you the property in this large signal measurements, right. Whereas, what you may want to do are what are called small signal measurements. Okay, where again right. So, I have this is B is my let us say response, sorry, B is my effect, A is my cause and some R is my response or property. R is something that I want to measure. Okay. So, then what I do now, or so I can the example will be Q equal to CV. Okay. Now what I do is instead of wiggling the entire voltage in the form of a sinusoid, what I am going to do is I am going to apply a DC bias. So, VDC, V equal to VDC plus a very small AC wiggling on the top of the DC bias, right. So, cos omega t. Okay. So, in other words, I am going to apply a DC voltage, a constant DC voltage, right. So, this is V as a function of time. So, I am going to apply a constant DC voltage and then apply a very small signal on the top of this. This VAC cos omega t is called the small signal. It is called small because VAC, the magnitude of VAC will be less than VDC. Okay. So, it is supposed to be small compared to the DC value. This is the DC value and VAC is supposed to be small compared to the DC value. Okay. Now, why is this nice and beautiful, right? Let us see. Then I have dq. Okay, so let us write again q equal to CV, right. Now C is a function of V, it is a non-linear capacitor, right, times V. Okay. So q equal to C of V, V is just VDC plus VAC cos omega t, okay, times VDC plus VAC cos omega t. This is my q. Okay. Now, since VAC is much less than VDC and as a result VAC times a number, this is less than 1, is also less than VDC, I can sort of ignore this, right. So, in V DC plus VAC cos omega t, if so I can just approximate this to be VDC. Okay. So, in other words so if VDC is 5 volts, VAC will be something like 0.1 volt, right. So, I can sort of assume that 5.1, 4.9, the variation is going to be between 5.1 and 4.9 and that I just assign this to be 5 volts. That is my approximation that I am doing. Okay. Then in that case Q is going to be C of VDC and VDC is not changing with time, right. This is time independent. Okay. Times VDC plus VAC cos omega t, right. Now, if I do dq, what is dq? dq is again C now so dq by dt, right. So, that is the current that I am going to measure is just C VDC, that is not going to change, right, times VDC itself is not going to change. So, the derivative of that with respect to time is 0, VAC omega sin omega t, that is the current that I am going to measure, right. Oh, now I have something which is quite cute, right. So what about dV by dt? dV by dt is omega VAC sin omega t. Okay. So, if I just do now dq by dV, which is just 1 divided by 2, that is nothing but C at VDC, dq by dV at VDC, right. So, the way so and this directly gives me the value of capacitance, right. It does not care about the time varying nature of capacitance, it isolates so the time varying part of the capacitance is in the AC term, which is a very small term, right, and the actual capacitance so the voltage variation of capacitance is in the DC term, right. So, capacitance at 5 volts is sort of considered to be the same as capacitance at 4.99 volts, right. So, that is the approximation that we have in the small signal analysis, which is a reasonable assumption. And so, I do not really care if the voltage is varying between 4.99 and 5.1, I just give that value as capacitance at 5 volts, right. So, capacitance is not changing with time, but it is changing just with the voltage, the DC voltage that is applied, right. So, then I can measure capacitance as a function of DC voltage and there I get these sort of plots, right. So that I just showed you. Okay. So, small signal measurement is something that so I can use to measure the capacitance as a function of voltage, right. Or any property for that matter, the direct way of measuring any property as differential change in the B being the effect by differential change in A, which is the cause, right. So, this is differential change in effect by differential change in cause, right, works only if my signal A, right, is varying in a small signal scheme, right. So, A equal to A naught A DC plus A AC cos omega t, right. So, that should be the variation and A AC should be less than A DC. Okay. So, only with small signal measurements I can directly take the change in the cause divided by the change in the effect divided by the change in the cause, and I can get the value of property, right. So, that is a direct measurement. If I do a large signal measurement, however, change in the the cause or change in the effect or change in the output divided by change in the input is not going to give me the property, right. It is property plus something else, especially if the property is non-linear. If the property is linear, both are one and the same, right. If the property is a non-linear property, then change in the cause divided by the change in the effect divided by change in the cause does not give me the property. Okay. So, that's something that that is a measurement protocol that people use. People just say small signal measurement. When they say small signal measurement, what you should understand is what they are actually measuring is the underlying property, right. So, they want to measure the underlying property. Okay. So, what comes out of the small signal measurement is directly the property which is the response function, which is capacitance, which is inductance, which is resistance, right. So, all these things come out of small signal measurement. Okay. Now, for example, how do I measure something like a piezoelectric property, right. So, piezoelectricity, what does it relate, right. So, or converse piezoelectricity, right. So, my forcing function there is the electric field, and what I end up measuring is the strain or displacement, right. So, this is the piezoelectric tensor, the relation of the piezoelectric tensor. Now, okay. So, electric field, to apply electric field I apply voltage across some capacitor, and so voltage divided by L will be the electric field, right. So, my forcing function is going to be voltage. Right. So, I have a capacitor and I am going to, this is some sort of a non-centrosymmetric material, and I am going to measure the piezoelectric property. So, so then I apply a source which is actually DC, I apply DC plus VAC sin omega t or cos omega t, right. So, that is what my source is going to be. Okay. So, my source is, it applies a constant VDC, but on the top of that it wiggles the AC. Okay. Alright, so that is the source, but what am I going to measure? I should measure the displacement of this membrane, right. So, I am applying in other words so I am applying field in this direction. So, E is applied in the so if this is my third direction, sorry, if this is my direction 3, E is applied in direction 3. And I am going to measure the vibration of this, right. So, the displacement up and down, right, of this membrane or of this material, and so what I am going to measure is the displacement. Now, I have already used D for D33. So, displacement I am going to use delta, right. So, I am going to measure delta 3. So, delta 3 or I am is the displacement, and delta 3 divided by the initial thickness of the material, which is L, that is the strain, right. So, L3, that is my strain, and strain is X33, correct. So, this is what I am going to measure. So I am going to measure the displacement and I am going to estimate the strain, right. So, X33 equal to D333 E3, right. So, So, what I end up measuring is this property called D33. It is one tensor element, right. So, of the entire piezoelectric tensor, right. So, third rank tensor. So, I am going to measure what is called D33. Okay. All right. So, how do I measure? Okay, I can apply a voltage waveform. So, I need to give V equal to VDC plus VAC cos omega t, right. But then I am saying by applying this voltage, I should measure the change in strain. I should measure x equal to so I should measure x3, x33, or in some sense delta 3, the variation of delta 3. Now, how do I do that? How do I measure displacements? And these displacements are typically in few tens of picometers in thin films, right, tens of picometer to up to a nanometer. Okay. So, I have to measure displacements which are also subatomic, right. Now, what is 10 picometer? 10 picometer is 0.1 angstroms, right. 100 picometers is 1 angstrom. So, I have to measure displacements in this scale. None of the structural measurements actually have this sort of a resolution, right. If you want to do TEM or whatever, I mean some sort of dynamic electron microscopy, I really cannot measure 10 picometers, right. So, even with the current day advances, the resolution of a transmission electron microscopy where you can directly see atoms is still 20 picometers. Okay. So, can I do 10 picometer measurement or sub 10 picometer measurements, right. So, especially if my piezoelectric effect is very small on a thin film, I should be able to measure some displacement, right. So, this displacement above its the average position, right. So, I should be able to do some sort of a measurement. So, I should measure d of delta 3, right, or that relates to d of x33, that is the differential vibration of the membrane. So, what is the displacement of the membrane, right. So, the membrane is going to get displaced, right. So, I am going to apply so a V DC plus on the top of VDC I apply a small AC voltage, and with respect to this what I end up getting is what I have to measure is a small the displacement amplitude. This is displacement as a function of again time, right. So, I should be able to measure this displacement amplitude, which is very small. Like I told you, it is going to be tens of picometer to about 1 nanometer. These are the types of displacements that we measure on really thin films, which are used in MEMS, microelectronic mechanical systems, right. So, which are used as devices in these systems. Okay. So, there is a technique, right. So, and that technique we take help of laser interferometry, right, to measure ultra fine displacements. Of the membrane, right. So, you have essentially a laser source, right. So, this laser source will come here, right. So, this is a partially reflecting mirror, which means part of the light goes this way and part of the light actually comes this way, or a beam splitter, right. But it will not reflect light that is coming from the so the opposite direction. Okay. So, this is a partially reflecting mirror. I have a laser source like this, and this laser sort of I have split the beam the laser beam into two different beams. This is first beam, this is the second beam. Okay. Now, the first beam the second beam goes and falls on your so again I will put another beam splitter here. This goes and falls, there is a lens, right. So, I can converge this beam and this goes and falls on your sample. This is my sample, right, and my sample is vibrating up and down, right. So, since my sample is vibrating up and down, I mean so even before the sample vibrates up and down, the sample will, because the sample has metallic electrodes on the top, right. So, this is my dielectric, this is metal, and this is another metal, right. Since my sample has metallic electrodes, it will start reflecting this light, right, and when it starts reflecting here, this reflected light would not pass like this, that is the nature of the beam splitter that I am using, it would rather change its direction, right. So, this is the reflected light in blue, right. So, the red light, red, I mean I am just doing a ray diagram, the red one goes to the sample and it gets reflected in blue. Okay. Now, I put another mirror here, right. So, a 45-degree mirror, I can just put it in red, right. So, the mirror will actually bring this down here, and here I put another beam splitter. That means that this light will go this way, whereas this light will proceed unimpeded, right. So, that is the nature of this beam splitter, right. So, I have with this beam splitters and mirrors I can make this simple interferometry setup, and I have what is called a photodetector here. So, now what is the photodetector? See, the photodetector is seeing two laser beams, right, beam so two laser paths rather. So, path 1, right. So, laser beam 1 or laser ray diagram 1, if you follow the ray diagram 1, interfering with ray diagram 2. It is interfering because they come from the same source, right, and since they come from the same source, the light which is split here maintains a constant phase difference, right. So, so there is some phase difference between this path and so this path which is mentioned here and this path which goes to the sample and then comes back, right. So, there is going to be some phase difference. So, my photodetector can measure the phase difference, right. So, photodetector measures the phase difference between the reference beam, which is the beam 1, and the sample interacted beam, the beam that has gone and seen the sample, that is beam 2. Okay. Now, what is happening to the sample? The sample itself is vibrating up and down, right. So, it is going up and down, up and down, up and down, right. So, with time the Z of the sample is sort of moving up, coming down, going up, coming down, and so on and so forth. So, if I just plot the displacement of the sample with time, the sample itself, this interface, right. So, this interface position, if I plot it with time, that itself is vibrating up and down. Okay. So, sample is moving up and down. As a result, the laser that interacts, beam 2, right, will have different paths, will have to travel different paths at different times, right, and beam 2 is going to interfere with beam 1, which is the reference beam, and that creates phase difference, right, or path difference, oscillations which are going to be like this. So, if I just plot path difference or phase difference with time, that also oscillates, right. But this oscillation, actually from this oscillation I can estimate the sample expansion and contraction. It is a very neat technique, and you will have that to a sensitivity of about especially if I am doing it at higher frequencies, right. So, about greater than 1000 hertz, if I am doing these measurements at greater than 1 kilohertz, I will have a sensitivity of picometer sensitivity. Okay. So, it is a beautiful technique, you can measure picometric displacements. If I measure displacement directly, I can measure the change in displacements, and I can do the small signal measurement to actually get change in displacements. So, delta of delta, right, or display so displacement is oscillating like this. So, this is delta delta as a function of time. So, I can get delta delta amplitude of it, right. So, which is the maximum divided by the delta voltage AC, right. So, or or amplitude of the AC voltage, which is VAC. So, because I apply VAC sin omega t, right. So, amplitude of the displacement signal by amplitude of AC voltage, right. Ideally I should divide this with the length of the sample and this also with the length of the sample, that gives me the strain, right. So, strain amplitude divided by electric field amplitude, but changes, right. So, these are deltas, change in strain, this is the wiggling amplitude, right. So, amplitude actually tells me that this is just the wiggling, this is the differential change in electric field with respect to differential change in strain, and that should give me D33. Okay. So, simple calculation, but slightly it is a laser interferometry measurement, but this is a neat way of estimating what the piezoelectric coefficients are, right. So, experimentally. Okay. So, with that let us stop here for this class. In the next class I will do a similar explanation about how to measure just the capacitance or the dielectric constant, right. So far we have set up the small signal measurements, and we will see how to measure the capacitance, and from capacitance we will see that sort of a measurement also gives you so what is the resistance, right. So we will so this is a very standard measurement for any property. It does not need to be D33 or capacitance or so it can be any property that relates a cause and an effect, right. So to estimate these properties we have to do some sort of a dynamical measurement, but this is going to be small signal measurement. You have to change the effect should have change with time, and that is possible because the cause is also changing with time, and I am going to look at the change in the effect with respect to change in the cause, right. So, all this works out if the change in effects and changes in causes are small, and hence small signal measurements work for measurement of any property. Okay. So, in the next class we will take the specific case of capacitance and so capacitance, how to measure capacitance. All right. So let us end there. Thank you very much.